All right, well, good afternoon. I'm in total denial. I'm looking outside and it's snowing. It's almost May and it's snowing. I guess you gotta love Michigan, right? So, Merry Christmas to you. All right, so the first thing I want to just review. So today is the last lecture on new material, so you've made it. So congratulations to everybody. Next week we will Monday, Wednesday. We're just going to talk about past topics, look at other examples, and I'm kind of going to be um, at your will, really. So whatever you want me to go through as I kind of review the different concepts, I'll do whatever you want. Okay, so this is it, and I want to really have this as a capstone experience that we're going to talk about all kinds of things today, but it's all related to intermolecular forces, and for that we have to remember how to determine whether individual molecules are polar or nonpolar. Okay, and so here's three molecules on your screen, and I want you to tell me if these are polar or nonpolar. And so the first step, so this, will be a final exam question. Uh, the first step for all these is you have to draw their Lewis structures. Okay? And so aluminum trichloride has how many valence electrons? So aluminum is in group 13, or group 3A, I guess we can say. And then chlorine is group 7A. So that's 21, 22, 23, so 24 valence electrons. Phosphorus for this one is in group 5A, chlorine again 7A, so that's 21 and 5 is 26 valence electrons. And then CHCl3, we've got 7A, 1, and 4A. And so that's 21, 22, 23, 24, 25, 26 valence electrons. Okay, so then we're going to put aluminum in the middle in this one. And then build up electrons on the outside. So that's 6, 7, 8, 9, 10, 11, 12. 1, 22, 23, 24. Okay, so that's the Lewis structure for aluminum trichloride. Phosphorus trichloride is, we're building up around the outside. And in this case, we have 2 more electrons to place, so they go around the middle. Okay. And then CHCl3, so carbon's in the middle, because it's, on an exam, I'll be more explicit, so just to let you know what's in the middle. I think everybody kind of gets it, but I'll put this in bold. Okay, so you know that's the one in the middle. Then you put these 4 around it, so you've got a hydrogen and then 3 chlorines. Okay, so that's 8, 9, 10, 12, 14, 3 to 4 to 5, 26. Okay, whoops, you can't see that. Okay, maybe on this side. All right, so what shapes? So, the first step for these is determine their Lewis structures, then determine what shape they have. And so for this one, aluminum trichloride, what is its shape? So, I mean, is it tetrahedral or, all those? I think we had like 5 or 6 different shapes. Yeah, so trigonal planar, yep. Okay, and then this one, what do you think? Phosphorus trichloride. So now you've got 3 things around it and a lone pair. Pyramidal. So trigonal pyramidal, yep. Okay. And then this one, four things around it is tetrahedral, right? Okay, so polar, nonpolar. What do you think? So aluminum trichloride. What about that one? So what was that? I didn't get that. Let me turn up the volume here. There we go.
Non-polar?
So did you say nonpolar?
Yeah.
Yeah? Yeah, correct. Yep. And the reason for that is because all of these dipoles cancel. Okay, so in that tug of war in three different directions, you're not pulling that aluminum in any one direction. It's staying the same. So that is non-polar. Okay. And then what about the second one? So now you've got the dipoles looking like this. Yep, so now they do not cancel in this case, right? So that is polar. Yeah, for that one. Okay. So in other words, they're pushing the phosphorus down, right? So you don't have anything from the top that offsets that. So it's a polar molecule. And then the tetrahedral one, those kind of look like this. And then it's also going that way because carbon's more. Yeah, so that, so tetrahedral is, so what do you think about this one? Yeah, so chloroform, before I say anything. Any ideas?
Non-polar?
So it would be nonpolar if it were symmetric, right? So if you had four chlorines around it, okay, then all of those would cancel. If I do these, right? Okay, but notice that...
Does the hydrogen do something to it? Is that what makes it polar?
Correct, yes. So in this case, it doesn't offset these other ones, right? So you've got different dipoles pointing in these directions, and the hydrogen, it's actually not even moving out. It's actually going in, right? Because carbon's more electronegative than hydrogen, okay? And so if you kind of look at these different dipoles, you can see that they don't cancel each other anymore. And it's all because you have broken the symmetry. Okay, so this now is actually polar. Okay, so remember that table that I gave last day, all the different shapes and whether it was polar, nonpolar, those refer to molecules that were symmetric. They had the same things bonded to the center. Okay, and as soon as you interrupt that with something else, now it instantly becomes polar. Okay. All right. So let's talk about then this rule. So like dissolves like, okay, and so this means that a polar or nonpolar solute, okay, depending on what their polarity is, and a solute means the substance that's being dissolved, okay, and then solvent is the substance that's in excess, okay, so think about it like, you've got water, and then you're going to put in, so this is H2O, and you're going to put in like salt or something like that. Okay, so this would be your solute, and this is your solvent. All right, and so we didn't really talk about this last day a whole lot, but ionic, so this is a metal and a non-metal. Okay, so this is an ionic solid. Those are really examples of polar. Okay, so they're extremely polar. Okay, so other types of polar compounds, they've got one end of the molecule. Like if we look at water, for instance, right, that was polar, And then you had, one end of the molecule that had a partial negative. These were positives, partially positive. With sodium chloride, for instance, it's sort of polar to the extreme, right? Because you don't even have the deltas anymore, right? It's full positive and negative. Okay, so these are really referred to as like the most polar you can have. Okay, and so they will definitely be soluble in polar solvents. Okay, and so with these that we looked at, that I've scribbled over here today, which ones of these do you think will be soluble in water then? So if you take aluminum chloride and you put it in water, is it going to dissolve or not? What do you think? So what do you think? So aluminum chloride, is it going to be soluble in water? So we said that aluminum chloride was nonpolar and water is polar. So that's an example, remember, so it's like dissolves like. Okay, so they don't match each other, so that means no. It's not going to be soluble. Okay? We say generally that it's soluble if you have like a gas or solid that's dissolving in a liquid is most common. We would say miscible. Have you heard the term miscible before? That's if you have like a liquid, two liquids, like oil and water, for instance. Okay, they are immiscible. Okay, so it's miscible, or in that case, it would be immiscible. Okay, so it would be like oil plus water, and then miscible would be ethanol. Okay, so this is ethanol in water. Okay. All right, so what do you think about phosphorus trichloride in water? PCl3. Yeah, it is. Yeah, and the reason for that is that we said that's polar and water's polar. So like dissolves like. Okay, and then likewise chloroform too. Right? We said that that's polar and water's polar, so that will be. Okay, so related to like this concept, that really is all I could ask on the final exam, right? Is just give you two different things, ask if they're soluble with one another, and for that, I'm really asking you to determine the polarities of both and see if they match. Okay, if they don't, then nope, they're not soluble, like this case. Okay, and if they do, then they're soluble. Okay. And then the other question would be, kind of like this, where, I ask you, give you a molecule and say, okay, is it polar or nonpolar? Okay, and for that you have to do Lewis structure, its shape, and then look at those dipoles and see if they cancel or not. Okay? So is everybody kind of cool with polar, nonpolar, these concepts? Any other questions here? Okay. All right, so let's talk applications. Okay, and here's one that I want to talk about. What do you think? So carbon dioxide in water, is that soluble or not? So CO2, so let me do this one. So water's that. Lewis structure, so that's bent. Lewis structure for CO2, remember, is this. Okay, so that's linear. So if this is polar, what do you think carbon dioxide is? Is that going to be also polar? Yeah, so that is definitely going to be nonpolar. Okay, because the dipoles, one is in that direction, one's in the other, and they cancel each other, right? So in that tug of war, the carbon is not going to be moved in any direction, okay? So you have nonpolar in polar, so they are not soluble or miscible with one another, okay? And so here's the application, and this is a fun one. You know, I wish we were face to face for many reasons, but you know, I miss seeing your smiles and, you know, laughing at my lame jokes, you know, in person. But this is a demo I really like to show in class, and it's something you may have seen before. This is a fun one you can do in your future classrooms. But Mentos and Diet Coke. Have anybody, have you seen this before? It's a can. So Mentos is this candy, and so yeah, I just want to kind of show you this short little video here, like a couple minutes, and show you what that looks like. And it's all exploiting that carbon dioxide is nonpolar, water is polar, and the CO2, you can get some to get into water, like in these carbonated beverages, but it really doesn't like to stay there. And so this is really exploiting that like dissolves like, that, you know, CO2 really doesn't like to be dissolved in water. Okay, let me just show you this.
Hey everybody, how you doing? Hey, have you ever noticed when you put a straw in your favorite soda that the straw gets a whole bunch of bubbles on it? If you look closely, you can see that the straw gets so many bubbles that it starts actually lifting up out of the cup. How about if you put something else in the soda? I don't know, like a pipe cleaner. Let's see what happens. Man, I think it's very, very bubbly also. Let's try one more thing. How about a candy mint called a Mento? Wow. So lots of bubbles form on the Mento also. You know, the bubbles are made from a gas called carbon dioxide. The soda company puts the carbon dioxide gas in the soda when they make it at the factory, and that's what makes the soda fizzy. But why does the carbon dioxide collect on the straw or the pipe cleaner or the glass for that matter? You know, if you could look way down at the Mento and the other stuff we put in there, they're not really as smooth as they look. You'd see that it has a lot of tiny little dents in it, and scratches, little bumps. So the carbon dioxide molecules collect on these little bumps, these little dents, and form bubbles. You know, there's a pretty cool activity you can do with a bottle of soda and a pack of Mentos. I mean, you guys saw that the Mentos candy had a pretty big surface where a lot of carbon dioxide formed and a lot of bubbles came up. It's easiest to do if you have a tube where you can stack the whole pack of Mentos. We made one out of construction paper and some tape. You slowly and carefully open the bottle of soda and put it down on a flat surface outside where it's okay to get stuff wet with soda. Then you put the open end of your tube of Mentos on a card and place the card directly over the opening of the soda bottle. And when you're ready, remove the card, let all the Mentos drop into the soda, and jump out of the way. Wow, that was cool. Those carbon dioxide molecules sure made bubbles in a hurry. Well, that was really chemistry in action. Hey, see you next time.
All right, so yeah, it actually works. And instead of a cardboard tube, if you use a test tube that has a diameter just a little bit bigger than the Mentos, and then you kind of like hold it with your finger and then dump it in at once. And so it's really a fun thing to do. I actually do it in the classroom, and then there's a lot of, I'm sure the janitors love me that week that I do it. But yeah, sometimes outside, is a lot better. But like in the winter time, it's not possible. So, but anyway, yeah, it's a fun one, and that is again exploiting this uh, unlike doesn't dissolve unlike kind of thing, where you've got nonpolar not being so soluble in a polar solvent. Okay, so that is kind of application one. Now, the next application I'm going to talk about today is opioids. Okay, and so this is something that's in the news a whole lot. Before this COVID-19, it was even more in the news. But yeah, this is. I'm going to show you a little video first about like kind of top down. How do these opioids give you this pain relieving function? And then I'm going to talk about the actual chemistry, so you can see that it is just exploiting these intermolecular forces. Okay, so here we go.
Coveted opioids for the euphoria and the pain. For centuries, societies have coveted opioids for the euphoria and the pain relief they provide.
In the 1800s, when chemists extracted morphine from opium poppies, it became the go-to treatment for the American Civil War.
After morphine caused widespread addiction, drug companies invented what they thought was a non-addictive substitute,
a cough syrup called heroin.
That turned out poorly for the 20th century.
Today, prescription opioids like fentanyl and oxycodone crowd America's medicine cabinets and its streets.
Opioid overdoses now kill more Americans every year than car accidents.
But to understand how we arrived here, you'll need to venture deep into the mind.
Here's why our brains love opioids.
When opioids enter the brain, they land on tiny docking stations at the end of your nerves called receptors.
Typically, the receptors catch chemical messengers called neurotransmitters to activate your nerve cells.
Opioid receptors do just the opposite. They stop electrical pulses from traveling through your nerve cells, also known as neurons.
This dampening is handy with pain relief. Say you have chronic back pain. Your inflamed muscles are constantly sending pain signals to your brain via neurons in your spine.
Opioids quiet those nerves, relieving your pain.
Opioids have three major receptors, mu, kappa, and delta. But the mu receptor is the one to remember.
The mu receptor is responsible for the consequences of almost all opiates.
It slows breathing, eliminates pain, and fills the mind with warm euphoria.
But too much of this opioid off switch becomes addictive.
Opioid addiction starts in the midbrain, where mu opioid receptors turn off a batch of nerve cells called GABAergic neurons. GABAergic neurons are themselves an off switch for pleasure.
They prevent other midbrain neurons from flooding the brain's pleasure circuits with another transmitter, dopamine.
It was definitely a party at first, and felt it was fun. No consequences right away.
At one stop along these pleasure circuits, the nucleus accumbens, the dopamine triggers a surge of happiness that reinforces the idea that opioid drugs are rewarding.
And in our brain's fear center, the amygdala, the dopamine relieves anxiety and stress.
Just an overall sense of well-being, no problems, just warm.
Decision-making brain areas become overwhelmed and cravings set in. All drugs come with a dark side as they clear the body. This is known as withdrawal.
Too much beer causes a hangover the next day.
Cheers.
What the hell?
A cocaine high is followed by a crash.
But opioids, especially long-lasting ones like methadone, don't change a person's outward behaviors. You can still drive and go to work.
I was a functioning addict. I worked at a real estate company. I was a broker over 900 agents.
However, opioids cause brain circuits to slowly adopt a new state of normal.
Soon, without opioids in the body, addicts feel constantly anxious, and their stress hormones stay elevated.
I just remember waking up and everything was blurry and I felt really bad.
Opioids typically trigger constipation and tweak body temperature. Remove them, and a person with opioid dependence has persistent diarrhea, hot and cold sweats, and goosebumps.
Some describe opioid withdrawal as the sickest feeling they've ever had, and the desperate hunger for relief drives addiction.
Well, I had an Oxycontin in my jean pocket and I couldn't find it, and I remember just crawling all around on the ground, and I didn't know what was happening to me.
Here's the dangerous kicker. The potency of opioids diminishes over time if you abuse them.
Eventually, rather than remedy your chronic back problem, your pain becomes linked with the emotional and physical toil of opioid withdrawal.
It becomes a vicious cycle. Popping more painkillers or injecting heroin more frequently becomes the way to keep all those bad feelings at bay.
Or if you started recreationally, the struggle against withdrawal becomes all-consuming.
You keep chasing that high, and you never get that original feeling again, and you kind of get immune to it, and then you're just maintaining, and then without it, you're sick.
Okay, so that's the problems with it. I guess how it works and why it's so addicting. So what do those structures look like? And so if we look at the chemical structures of these, they all have, you can see a very, very common structure, okay? And these are everything, so there's really two varieties. There is this one that I guess the only real difference is you've got a double bond here. So these are all carbons in the structure. So if they're not labeled, there's carbons here. And then you've got hydrogens that aren't shown. And so this would be a carbon-carbon double bond and then some hydrogens here. And this variety you don't. And then you've got just different substituents, so different groups that are bonded to carbons in these different cases. Okay, and so morphine, codeine, heroin, all of those, all that they differ by is just, instead of R1 being hydrogen in morphine, codeine, it's CH3. Okay, so you just the few different atoms difference, and you have very, very different behaviors. Like codeine is something you can get, with a prescription quite easily. And, even some cough suppressants have, smaller amounts of codeine in it, whereas morphine is like severe pain relief. And it's very similar in structure, just really with just the one group difference, okay? And then the other ones, like, the Netflix series, The Pharmacist that's going on now, it's all really about OxyContin, which is the trade name of oxycodone. It's, what largely was responsible for Michael Jackson's death too. He was really, really addicted to this. And it has this structure where you've got these different groups. R1 is a CH3 off of here, a CH3 off of here. Let's see, an OH here, and a hydrogen off of here. Okay, so kind of to put those, it's kind of hard to visualize these dashed or darker lines means that all this is kind of on the plane of your computer screen, and then this is coming out at you. But I did, there's something called MolView, molview.org, and this is something for your classrooms to incorporate as well, because what's really nice is you can kind of move them around. And so this on the left is heroin, okay, and then on the right I've got something called, it's the trade name is Narcan, and so this is what police or medical personnel what they carry around with them at all times in their glove compartments, is used for, if someone is ODing on heroin or some of these drugs, that they will inject them with this. Okay, and it actually, I'm going to show you here, the behavior of it, but basically, you've got these receptor sites, and morphine or Oxycontin, all these will bind to these receptor sites. And if you introduce Narcan, then this actually has a much stronger binding for that receptor site. And so this will preferentially bind to that target and then will release the drug from your system. And so it's really, really fast reacting. And you can see, as far as like the shape or the structures, they're quite similar, right? So this is where you have, that the red, by the way, in all structures, red is for oxygen, gray is carbon, and white is hydrogen, and then blue is nitrogen. Okay, and so you've got, a similar kind of backbone in the Narcan molecule, just different substituents. So you just have different groups off of here. So this one is kind of a more simpler structure, whereas heroin, you see all these extra groups on here. And so that's why this will bind a lot easier, because it doesn't have all these other groups that will kind of, bounce around and detract from its binding. Okay? And so the binding process, it's quite complicated, but it really isn't, if you kind of boil it down to our intermolecular forces. And so remember last day, I talked about really three varieties, right? There was London dispersion, and that was the force between nonpolar molecules, okay? And so if you look at this structure, the nonpolar part would be all the carbon backbone. So all this stuff here in the structure is really just carbon, hydrogen. So it's just really a hydrocarbon group, a whole bunch of groups. And so this we call hydrophobic because it doesn't like water. It's, again, nonpolar and water's polar. And so the way this is kind of color coded is this, I don't know, like a grayish yellow. This is the protein pocket where it's really the binding site. So this is where these drugs will bind to. So these are the receptor sites in your brain. And so this is nonpolar. And so you'll see that's where all this kind of framework will kind of sit in that pocket. Okay, whoops. And then what really corresponds to strong binding is then hydrogen bonding. And so that's between, if you have like an OH or an NH, those will bind really strongly with these what we call dipole-dipole interactions. And so you'll see this is, I guess, heroin, and then something similar to Narcan on the right. Okay, and so you can see heroin binds, these are amino acids, okay, and so all proteins are made up of these just different chains of amino acids. And so the binding site is just a big protein. And so it actually, the drug interacts with individual proteins or individual amino acids in the protein structure, and that's all by hydrogen bonding. Okay, so this is one amino acid with an OH group. The hydrogen isn't shown here, it's just the oxygen. And then this is the drugs, this is heroin, and you've got a hydrogen bond here and a hydrogen bond here. And so really strong binding to that protein, or that part of the protein. And then this is another amino acid residue, aspartic acid, okay, and it will bind to this part of the drug, which, remember, NH is also something that can hydrogen bond, okay? And so you've got now this group, an OH with an NH, so this is also really strong hydrogen bonding, okay? And then this is how the Narcan or I guess the drug that's given to prevent ODing. If they give it right away, then you get binding again through hydrogen bonding. Okay, this is a different amino acid, and that will bind with the OH, or I guess just an oxygen here. Okay, so an NH with an O here. And then you've got hydrogen bonding here to this amino acid. So you've got all these different types of amino acids that kind of wrap around the drug and hold it in place. And you can see this Narcan, when they inject it into this person who's about to die, it's now binding to 3 different amino acids. And so you can say that it's more strongly bound than the heroin, which was just really bound to 2 different amino acids. Okay? So any questions about that? It's all related to just hydrogen bonding between these OH and then whatever particular groups are on amino acids in this protein. Okay? So when you look at a chemical structure, you can instantly see the different sites that are strong binders. And so you've got, anytime you have an OH, an NH, or an FH, those are really strong binding sites by hydrogen bonding. Okay, so you've got really 2 sites for hydrogen bonding, and then another one here. So this is, it's not shown, but you're going to have an NH off of here too. Okay, and so that's also a site that can hydrogen bond. And then this Narcan, you can have NH and then an OH here and an OH there. Okay. All right, so what's interesting is that fentanyl is, I guess it came from China is what people figure, that it was synthesized there first and then came over here in large amounts. And the problem with it, so it's not a natural compound. So really none of these, like OxyContin, all these are synthesized in laboratories. Fentanyl has a very different shape or different structure. So it looks a lot different. It's a lot simpler, right? I think you'd agree this versus, where was the other one? These ones, right? Where you've got all these rings fused together. This is a much more complex shape. This one much simpler. And so that means that it's much easier to synthesize. And it turns out this is much cheaper. And so the problem is that people, since fentanyl's cheaper, they would put in bits of fentanyl in with heroin. And so people would, drug abusers would put in heroin thinking that it's pure heroin, but it's got fentanyl in there. And this is 50 times more addictive or dangerous, lethal, than morphine. Okay, and so this is much more addictive and dangerous. And so if it's laced with this, then people were overdosing. And so fentanyl, kind of the lethal dose of this, in comparison, this is really something, so this is, if you were to ingest this much heroin, which really isn't that much, so these vials are really small vials, that would be enough to kill one person, okay, an average person. This is how much it takes to kill an average person of fentanyl. Okay, so just a few granules. And then this is carfentanil. So this is another derivative of it. It's a structure similar to fentanyl, but so much more dangerous. And so this is what that looks like. Okay, so this is compared to morphine. Fentanyl is 50 times more lethal. Okay, and so the only difference between fentanyl and carfentanil is, again, just one substituent. So you replace a hydrogen with this group, and because of this, now you have stronger hydrogen bonding with the receptor sites in your brain. And now, instead of it being 50 times more dangerous than morphine, it's 1,000 times more dangerous. Okay. And so that's why, just a few granules is enough. But if you think it couldn't get any worse than that as far as dangerous, there's something even more potent. And this is really the opioid so far that is like the most lethal. And it's called omefentanyl. And so some people call it oh my fentanyl just because it's now 6,300 times more lethal than morphine. Um, and so it requires, a little, it has a few different substituents. Okay, so now I guess just two different groups, one off of here and one off of there. And just that little change in its structure is enough to cause an amazing amount of difference in how it binds to these receptor sites. And so, what's scary about it is that 1 ounce of this compound is enough to kill half the population of the US. Okay, so just think about that. If you had like 1 ounce or 28 grams, you could kill half the people in the US. And what's scary about it is, for, people that have, like terrorists, etc. Here is the synthesis that is widely available. This is just for fentanyl, but you can get the synthesis in journals for this thing. Okay. And so that just scares the heck out of me that, somebody could get this and put it in water supplies and, take out half the people in the US. And so it's pretty scary stuff. Okay. But what's dangerous, or what's, I guess, amazing, is that it's different just by just really one or two substituents. Okay. All right. So the last application I want to talk about is something we're dealing with, daily basis now, is how does soap destroy the coronavirus? Okay. And that is, again, like dissolves like. Okay. And so if you were to look at soap, this is an example of a soap particle or molecule. You'll have part of the molecule that is just carbon with either carbons or hydrogens bonded to it. So this is just, each of these carbons are tetrahedral, okay? And they're bonded to, two things on one side and two different things on the other side. So these are really nonpolar, okay? So this whole backbone is nonpolar. And then you've got this part where you've got a carbon, oxygens, and an oxygen hydrogen here, COOH group, that is polar. Okay, so this part of the molecule will be dissolved in water. This part will be dissolved in like oils or something nonpolar. Okay, and so when you're thinking about, detergents, like when you're washing clothes or dishes, this part will wrap around the oil in your clothing or on your plate. And then this part will mix with water and it pulls it, pull this will then pull your oil from your clothing into the water. Okay. And so likewise, if this is what coronavirus looks like, okay, you've got just some nucleus or cell here that's covered with protein that is really just kind of like an oily layer. Then you introduce soap. Okay, and so this is why, they tell you to wash your hands, sing happy birthday 2 times or something like that is what they're saying. Like take your time and make sure you lather up the soap lots on your hands. And that's giving it time for this hydrophobic or the nonpolar tail to interrupt the structure with this kind of oily surface that coronavirus has. And so these chains kind of break it apart. And now these balls, which are the polar part, they will then take all of this, it sort of surrounds them like this. Okay, so we call it a micelle, where you've got all the nonpolar chains that kind of go around the leftovers now of the coronavirus. And then this is washed down the drain, okay, because this is now soluble in water, okay? And so that's how soap not only just kind of wraps around the coronavirus and washes it, kind of removes it from your hand, it actually destroys the structure of it, okay? And so then, hand sanitizers have a similar effect, but they're, in general, if you use just hand sanitizer, then it's not really being washed off your hand. It's not under flowing water. And it's only as effective as long as it doesn't evaporate from your skin. And so, alcohols are volatile, which means they evaporate pretty easily. And so if you're just using hand sanitizer, it won't work very long until, it's off your skin. So you have to reapply really often. Whereas soap, you wash it off, and then I guess, as long as you're washing your hands frequently, then, any additional coronavirus that gets on your skin, you can wash it off again, destroy it and wash it off. Okay, so kind of a whirlwind tour of different applications, all related to like dissolves like, or like binds to like, I guess, in like opioid functions. But it's all related to like polar, nonpolar, and then in particular, these intermolecular forces of hydrogen bonding, dipole-dipole, or London dispersion forces. Okay. All right, so any questions about anything? No questions before we sign off then? All right. Well, enjoy the rest of your day, and we will touch base again next Monday with a review for the final. All right, take care.